Hello again, welcome back. Today in section 4.3 we're going to be talking about logarithms. I'm going to show you what a logarithm is, how to evaluate a logarithm, and we're going to solve a few log equations together, and we're going to talk about properties of logarithms. Here we go. Now you'll remember that the previous section dealt with exponential functions that looked like this: y equals a to the x. And remember we said a couldn't be 1. If you remember the graphs of the exponential functions that we looked at, they did pass the horizontal line test, so we know that exponential functions are one-to-one, and therefore we know that exponential functions can have an inverse function. Now remember how we find an inverse. To find an inverse function, we exchange x and y in the equation that defines the function. So if we start with y equals a to the x, and we exchange the x and y, we'll end up with x equals a to the y, which is our inverse function, but we don't have a way to solve it for y. That's the problem. We need a way to be able to solve this for y, and that's where logarithms come in. To solve for an exponent, we use logarithms. This is basically the definition of a logarithm. If we have an exponential equation that says a to the x equals y, we can rewrite that in log form, so it says log base a of y equals x. You see, a log is basically an exponent. Pretty much this expression says the exponent of a that gives us a y is x. And that's the same thing this one says too. The exponent of a that gives us a y is x. So log base a of x represents the exponent to which the base a must be raised to obtain x. Always remember that a log represents an exponent. If you'll keep that in mind, it helps the whole section go much better. Now we're not going to evaluate logs yet, but let's just take a few exponential expressions and practice rewriting them in log form. So this says 2 to the third equals 8. Well, the base here is 2 and the exponent is 3. So we're going to rewrite this as log base 2 of 8 equals 3. So remember, an exponent is a logarithm. So you see how this log expression is equal to our exponent? The exponent of 2 that produces an 8 is 3. And that's what this says too. The exponent of 2 that produces an 8 is 3. Okay, let's look at this one. 1/2 to the negative 4th power equals 16. So the base is 1/2 and the exponent is negative 4. So we're going to write log base 1/2 of 16 equals negative 4. Remember, a log is an exponent. Okay, here we look at part C. 10 to the 5th power is 100,000. So the base is 10 and the exponent is 5. So we would say log base 10 of 100,000 equals 5. And I'll have a little more to say about log base 10 later on. Now this time, let's take the log expression and let's rewrite it in exponential form just to make sure we can go both ways. So this says log base 3 of 1 over 81 equals negative 4. So the base is 3, and we remember that a log is an exponent. So this is going to become 3 to the negative 4th power equals 1 over 81. And this one says log base 5 of 5 equals 1. So this is going to become base 5, the exponent is 1, and the other side is 5. And we know that's true. Okay, this one says log base 7 of 1 equals 0. So the base is 7, and the exponent is 0, and the other side is 1. Now it's really important for you to be able to take a log equation and write it in exponential form, and also to take an exponential equation and write it in log form. It's very helpful to us to be able to switch back and forth, and you'll see that as we get into our log equations later in this section. Now we're finally ready to start evaluating logarithms. And I want to just let you know up front that your calculator can't really do this for you, because even though it has a log button on it, that is log base 10. So your calculator does not really have a way to do log of any other base, and here we have lots of different bases. There is a formula you can use, but we're not going to cover the formula because what we're going to do is just really simple. So let's start here with part A. We have log base 3 of 81. Well, remember that a log is an exponent, so it might help you to see this in exponential form. So the base is 3, and we're looking for the exponent, and we want to know what is the power of 3 that will give us an 81. Well, when we think about it, we know that the fourth power of 3 is 81. So the log base 3 of 81 is 4. Let's do the same thing on part B. Log base 3 of 1/3. So the base is 3, and we're looking for the exponent. And we want to know what is the exponent of 3 that will give us a 1/3. So we know that 1/3 is just the reciprocal of 3. So what is the exponent that will give us a reciprocal? And that exponent is -1. So the log base 3 of 1/3 is -1. Here's part C. It says log base 6 of square root of 6. So I have to say to myself, what is the exponent of 6 that will produce the square root of 6? And if you want to write it in exponential form, that helps. So it says, what is the exponent of 6 that will give me a square root of 6? If you still don't know, you might try writing this right side with an exponent instead of a radical. And you know that the square root of 6 is the same as the 1/2 power of 6. So what is the power of 6 that gives you 6 to the 1/2? Well, that power is 1/2. And here's part D. Log base 3 of 27 to the 3/2. So we would say, what is the exponent of 3 that produces 27 to the 3/2? That one's kind of hard to think up in your head, so it really does help to see it in exponential form. And then you know that if you could just have the bases the same on both sides, you would know the exponent. So let's write this 27 as 3 to the 3rd. And we know that our power rule says we can multiply these exponents together. So we see that 3 to the power we're looking for is 3 to the 9/2. So the power we're looking for is 9/2. So the log base 3 of 27 to the 3/2 is 9/2. Here's part E. It says log base 1/2 of 8. So the base is 1/2, and we are looking for the exponent of 1/2 that would produce an 8. In other words, 1/2 to what power equals 8? Well, if you think about it, we know that we're going to have to do a reciprocal of 1/2 to get our 8 here. So 1/2 to the -1 power is 2, and then to get from 2 to 8, we need the 3rd power. So we need the -3rd power. Now, if you want to check that you're correct, what you can do is write down 1/2 to the -3. Now you know that the negative is going to cause a reciprocal here, so we have 2 to the +3, and that does equal 8. So it looks like -3 is the exponent we were looking for. And here's part F, log base E of 1/e squared. Well, when we look at it in exponential form, it says e to what power equals 1/e squared. Well, we know that in order to get it squared, we're going to have a 2, and we know that in order to get it to the denominator, we're going to have a negative. So e to the -2 gives us this expression, so this log is -2. We're going to get a little more practice evaluating logs, but before we do, I just want to give you a little piece of information. Logs were developed actually to make multiplication easier, and for a long time before the development of handheld calculators, that's what they were used for. People used to have tables of logs that they would use to help them multiply large numbers together. So the log tables came to be written in base 10. So base 10 became known as the common base. So even today, if you see a log expression without a base, they're using the common base, and so you can assume that's base 10. Now let's do a few more practice problems evaluating logs. You might pause the video and try these on your own, but I'll go through them with you now. So here we have log base 4 of 1 over 64. So if we write that in exponential form, what is the power of 4 that gives us 1 over 64? Well, we know it will have to be negative, and we know that 4 to the third is 64. So this log is going to be negative 3. And then this one does not have a base, it just says log of 100. Well, we know that whenever a log is written without a base, it's log base 10. So we can write 10 to what power equals 100? Well, we know the power of 10 that makes 100 is the second power. So the log of 100 is 2. And again, remember that the log button on your calculator is base 10. So if you were to punch in log of 100, it should give you a 2. Now let's look at part C. We have log base square root of 3 equals 81. So I'm going to write this in exponential form, and it will say square root of 3 to what power equals 81. Well, on this one, I found it helpful to write both sides with the same base. So I'm going to write square root of 3 as 3 to the 1/2, and I'm going to write 81 as 3 to the 4th. So 3 to the 1/2 raised to some unknown power equals 4. Notice here that the bases are the same, so 1/2 times this unknown number equals 4. I'm going to write that in equation form, and then to solve this equation we could just multiply both sides by 2, and we would see that x would have to equal 8. So the log here that we were after is 8. Now let's look at log base 7 of 49. This one's pretty simple, so we could put 7 to what power equals 49. You probably don't even have to write that one down. You know that the power of 7 that we need is 2. And now let's look at part E. We have log base 25 of 5. So to write it in exponential form, we would say 25 to what power equals 5? Well, we know that the square root of 25 equals 5, and we know that the square root is equal to the 1/2 power. So 25 to the 1/2 equals 5, so the log base 25 that we're looking for is 1/2. And here we have log of 1 over 1,000. So this has got to be log base 10 of 1 over 1,000. So we're trying to say what is the power of 10 that will give us 1 over 1,000. Well, to get the 10 to the denominator, we would need a negative, and to change from 10 to 1,000, we would need a 3. So 10 to the negative third is 1 over 1,000, and the log we're looking for is negative 3. Now we're in example 2, and we're ready to start solving equations. And I'm just going to go ahead and tell you that the trick to solving all of these equations is to write them in exponential form, because you got to get rid of the log notation somehow, and the way to do that is always to write it in exponential form. So here we have log base x of 8 over 27 equals 3. So let's write x to the third equals 8 over 27. And now to isolate x, we'll need to eliminate this 3 exponent, so we'll take the third root of both sides, and we'll have x equals the third root of 8 over 27, and the third root of 8 is 2, and the third root of 27 is 3. Here's part B of example 2. We have log base 4 of x equals 5/2. So again, the trick is to write this in exponential form. So let's have base 4 to the 5/2 power equals x. And now you could evaluate this on your calculator, but I hope that you'll do it with me just mentally. Let's recopy it so we can do a little scratch work, but it actually can be done totally in your head. Remember that the denominator of the exponent tells us what root we're taking. So the 2 represents the square root. And we'll say square root of 4 is 2. Now that's going to leave us 2 to the 5th because basically the 2 is used up. So the square root of 4 is 2. Now we have 2 to the 5th. And we know 2 to the 5th is 32. So the x that we were looking for is 32. And now let's try log base 49 of the cube root of 7 equals x. Again, the trick is to go to the exponential form. So we'll say 49 to the x equals the cube root of 7. And now I see that both of these bases are related to 7. So let's write the left side as 7 squared raised to the x. And let's write the right side as 7 to the 1/3. Now we know that the power rule tells us that these two exponents will end up being multiplied together, so we would have 7 to the 2x equals 7 to the 1/3. That means 2x equals 1/3. And to isolate this x, all we have to do is divide both sides by 2. And I'll just put this 2 in the existing denominator. No need to create a new denominator. And that's going to give us x equals 1/6. Here are a couple more equations for us to practice on. Let's switch these into exponential form. So we'll have 8 to the x equals the 4th root of 8. Let's remember that the 4th root means the 1/4 power. And then we can say 8 to the x equals 8 to the 1/4. So x must be 1/4. And that's our solution. Now if you would try this one on your own, and now I'm going to go through it with you. It says x equals log base 6 of the 3rd root of 6. So we can write 6 to the x equals the 3rd root of 6. And we know the 3rd root is the 1/3 power. So we have 6 to the x equals 6 to the 1/3. And x equals 1/3. Now here we have a couple of equations that are not really log equations, although they do contain log expressions. So what we can do to solve these is take them out of the exponential form that they're in and write them in log form. And so let's try that. We've got x equals 2 to the log base 2 of 9. Let's change it into log form. So we would say log base 2 of x equals this exponent, which is log base 2 of 9. Now you can see that we have logs on both sides. So if it says log base 2 of x equals log base 2 of 9, then it must be true that x is the same as 9. So that's our solution, x equals 9. And not only that, but it gets a little better. We can kind of take a shortcut here. You may remember at the beginning of the section we talked about how log functions and exponential functions are inverses. That means that one of those functions plugged into the other one is going to simplify to x. Now what we've got here is a log base 2 function with a 9 plugged into it. So I've got 9 plugged into my log function, and then I've got that answer plugged into my exponential function. So the log function and the exponential function just undo each other, leaving us with a 9. Let's try that over here. So instead of going through all of this, we'll just remember that these two are inverses, so what we plug in has to come out. So we've got 7 to the log base 7 of 3. I remember that the log function and the exponential function are inverses, so they're going to undo each other, and we're just going to end up with, as our solution, x equals 3. That's all there is to it. Here are some more log equations that look a little different than the first ones we did, so I just thought we'd try these together. This one says log base x plus 3 of 6 equals 1. So let's write this in exponential form. We'll have x plus 3 to the first power equals 6. And now the first power means that we really don't even need the parentheses. So we've got x plus 3 equals 6. Just subtract 3 from both sides and x equals 3. Now here's part B. We have log base 1/3 of x plus 6 equals negative 2. So let's write 1/3 to the negative 2 equals x plus 6. And now let's evaluate this left side. We know the negative is going to cause a reciprocal here, so that will give us 3 to the second, which is 9, equals x plus 6. Now let's subtract 6 from both sides, and again x equals 3. And let's try this last one. This is one you could try on your own if you want to. We're going to have log base x minus 4 of 19 equals 1. So we write base x minus 4 exponent 1 equals 19. So now we say, well, the first power doesn't really do anything, so it's just x minus 4 equals 19, and add 4 to both sides, and we have x equals 23. Now let's look at some properties of logarithms. Since logs are essentially exponents, they behave according to exponent rules, but these rules are going to look a little bit different when we write them in logarithm form. What we're going to find out is that logs can be expanded into multiple terms or condensed into a single term using these properties. So now let me show you the properties. The first one is the product rule. It says that log base b of a product is equal to log base b of the first factor plus log base b of the second factor. So we can take one log expression and split it into two separate terms. And we also have the quotient rule, which says log base b of n over m is equal to log base b of n minus log base b of m. So notice that whatever was in the denominator of our argument, we end up having in a subtracted term. And the power rule says that log base b of x to the m is equal to m times log base b of x. Now, this looks a little bit surprising, but it's really just an extension of our product rule. Let's replace the m with a 2. So let's look at log base b of x squared. Well, x squared can be written as x times x. And then because this is a product, we can use our product rule to split it into two terms. And then I have 1 log base b of x plus 1 log base b of x. So that's just 2 log base b of x. And you see that our 2 that was an exponent ends up being a coefficient. So now that we see the properties, let's practice with them just a little bit. Now this is example 5, and all it says is rewrite each expression. So we have log base 6 of 7 times 9, and now this is a product, so we can use our product rule on it. I can split this into two terms. So I'm going to have log base 6 of 7 plus log base 6 of 9. And that's all they're asking us to do. So they said rewrite each expression. What they mean is expand this into multiple terms. And let's do the same thing on part B. We have log base 9 of 15 over 7. So let's expand this into two terms. We'll have log base 9 of 15 minus log base 9 of 7. And the second term is subtracted because the 7 was in the denominator. Continuing with example 5, now let's look at log base 5 of square root of 8. So of course we need to take the 8 out of its radical and write it as log base 5 of 8 to the 1/2. And now we can use the power rule to move the 1/2 power down to the coefficient position. So we've got 1/2 log base 5 of 8. And now let's look at part D. We have log base A of the cube root of m squared. Well, the first thing I would do is take that cube root radical away and write this as the 1/3 power. And now I would say that 2 times 1/3 is 2/3. So I have log base A of m to the 2/3. And now I would use my power rule to bring that down to the front, and we'd have 2/3 times the log base A of m. And let's look at part E. This has log base A of mnq over p squared times t to the fourth. Now what you need to understand is when we use the product and quotient rules, any factor that came from the top of our argument is going to produce a positive log term, and any factor that comes from the bottom of our argument is going to produce a negative log term. So knowing that, let's split this into 3 positive terms and 2 negative terms. We'll have log base a of m plus log base a of n plus log base a of q, and these next two will be minus. So we'll have minus log base a of p squared minus log base a of t to the fourth. And again, the m, n, q terms were positive because they came from the top. The p squared and t to the fourth terms are negative because they came from the denominator. And now we need to use our power rule to move these exponents to the front. So that's going to be log base a of m plus log base a of n plus log base a of q minus 2 times log base a of p minus 4 times log base a of t. And finally, this last part of example 5, let's look at log base b of the nth root of x to the third y to the fifth over z to the m. Now the first thing we would want to do is get rid of this radical, so I'll rewrite this nth root as the 1 over n power. That's going to give us log base b of x to the third y to the fifth over z to the m, all to the 1 over n power. And now I want to apply that 1 over n power to each factor inside the parentheses. That's going to give us log base b of x to the 3 over n, y to the 5 over n, over z to the m over n. And now we are going to use our product and quotient rules to split this into 3 terms. The x and the y will be positive and the z term will be negative. So we'll have log base b of x to the 3 over n plus log base b of y to the 5 over n minus log base b of z to the m over n. And now let's use our power rule to move these exponents to the front. That'll give us 3 over n log base b of x plus 5 over n log base b of y minus m over n log base b of z. And for example 6, let's go the other direction. Now we have multiple terms and we want to condense them into one single term. So the instructions say write each expression as a single logarithm with coefficient 1. So we know from our product and quotient rules that if a log term is positive, it must belong to the top of the argument, and if a log term is negative, it must belong to the bottom. So first, notice that we have all the same base here. You cannot do this with different bases. And now let's combine this into one log base 3 term. We'll have x plus 2 times x in the top. Remember, we're using our product rule, so these are multiplied together. And we'll have 2 in the denominator. And really that's it, but we could distribute the x just to make it look nice. And that's all. And let's try that on part B. Now notice on part B we have coefficients. So those coefficients will have to be put back in their exponent position. So first we're going to have log base a of m squared, and then we're going to have minus log base a of n to the third. And now because this is a minus log term, this n to the third is going to go in the denominator. So now I'm going to have one log base a term, and the argument is m squared over n to the third.